Thank you. All right. So the dot product we defined in two ways. The first one was the component-based product, A1, B1, A2, B2 plus A3, B3, right? So it is going to be scalar, as you know. When you multiply the two vectors, the result is going to be scalar. That is why it is called the scalar product as well, if you remember. The other form of to write this definition was this one, cosine theta. And then theta was the angle between these vectors. What else did we learn? And we use this one.
Vector and scalar projection.
Say it again?
Vector and scalar projections.
Exactly. We learned, right, the projection of u to the v to the onto u, and then that was given by this operation, right? That was the formula. This is the vectorial actual projection, if you remember. So we were projecting the v onto u. That's this vector p, the vector p. P is equal here, this one. And then later we saw that we can use the dot product to calculate the work, right? To calculate the work. Work can be calculated using dot product. So if we apply this force rate for this distance, the work you do can be calculated by dot product. This is just a small summary, actually, what we did in the previous class. Did I miss anything? You would like to add?
We talked about how to tell if an angle is orthogonal.
Say it again, Will. I couldn't hear that.
We talked about if an angle is orthogonal or not by telling, you could tell if the dot product equals 0.
Yeah, when it is equal 0, when you have, right, as a general feature, if you have two vectors, which they're orthogonal to each other, so you can say that the dot product is going to be 0 because of the right theta, since the theta is pi over 2. If you apply the formula, basically you are going to get this feature. So that's one of the nice features you always use, right? All right, guys. So this is just a small summary for today. If you remember, right, we just mentioned in the previous class, we said that we can multiply the vectors in two different ways. There might be some other ways, actually, but we don't want to use in this class. The other way is the cross product. So the topic for today is going to be the cross product. And I will show you again, like in the dot product, okay, we will have the two different definitions for the cross product. And we will see that if you would like to, okay, calculate the cross product, we will use the determinant form. I hope you have seen the determinant at high school, but I will review it actually today. So let me give the basic definition of the cross product. Cross product. First of all, when we say the cross product, I have two different vectors. Look at that. Yeah, let me take this one, V, and then U. And then I have an angle between them. This angle, the initial point of this angle actually is the U vector, and then the end point of this angle is the theta. if you apply the right-hand rule, what we mean by right-hand rule, your fingers needs to show the angle direction, all right? Your fingers needs to show the angle direction. As you see, the direction is positive, right? The direction of the theta is the positive. Where do I know that? Since if I go to the right, the counterclockwise, and that shows me the theta angle is the positive angle. So that is why if my fingers show that way, the cross multiplication actually gives me a perpendicular vector. In this case, okay, this vector, now we will define right now, but geometrically, this vector will point, okay, toward us. So it is gonna be the perpendicular vector to the, okay, this UV. If I show this in the 3-dimension, you can see in this way, guys. So let's say I took a U and V. I specifically chose they are in the same plane, okay? You don't need to choose in this way to show you, okay, what do we mean by cross product. Look at that. So this is the theta, let's say, right-hand rule. Now, the cross product of UV should be orthogonal to UV, okay, by the right-hand rule. So this is the right-hand rule. Your right, the fingers shows the way of the theta direction. The cross product of these two vectors should be orthogonal to the both vectors. Of course, those vectors doesn't need to be at the XY plane. It is just the example. But when we put those two vectors in the same plane, okay, the cross product is going to be the perpendicular vector to that one. So now I'm going to give you the official definition. All right. The cross product of vectors. Actually, this definition is the result of the second definition. You can prove that one, but you can give as a definition as well. U and V is denoted by U times V if U and V are not parallel. Then if they are not parallel, this is our definition, sine theta times n. It looks like the dot product definition, right? The second definition. As you see, this time I use the sine theta instead of the cosine theta, but I have another vector here. That vector where 0 is between, theta is between 0 and pi. We know that that's the angle between U and V. As you see, guys, this multiplication, the length of U, length of V, and then sine theta will produce what? Will produce a scalar. What I need a vector. Since the cross product should give me a vector. What type of vector I have here? As you see, it is a perpendicular vector. That is why the n will be chosen, okay? Will be chosen in this way. And n is the unit vector perpendicular to both u and v in the direction given by the right-hand rule. All right, let's go over the definition one more again. Understanding definition is the most important part of this topic. Like I said, this definition actually will not be used in the component. Yes, Ali, you can say the normal vector as well. As you see, U and V are just the two different vectors. If you use this definition right, when you multiply in this way, it's gonna be scalar. To make this as a vector, since I'd like to, get a vector after the cross product, opposed to the dot product, since dot product gave me scalar. This product should give me a vector. That is why I need to multiply, by another vector, n. And I know that the feature of the cross product is being, orthogonal, or the perpendicular. In other words, they call the normal vector. That is why n should have these features. N is the unit vector and also perpendicular to the both u and v. You might ask, why do we need should it be the perpendicular? Since the original definition, this is the, look at that, this is also definition, but there is another definition which I'm gonna show it to you soon. You will see that the basic cross product, well, what we mean by cross product, you just basically distribute each point together and then you multiply them. That definition actually requires me to have this, unit and then perpendicular vector here, right? That's how you need to look at the definition. And then this perpendicular vector can be determined by the right-hand rule, as you see, This is, by the way, these are now, as you see, orthogonal to the u and v. All right. We talked a lot about the definition. One more thing. Now, as an example, maybe. So can you please tell me right now, if u and v is parallel, what is u times v? Just write the basic result of this definition, guys. Basic consequence of this definition.
Is it going to be 0?
It is 0, right, Ben? How? Since you define this in this way, the u v length and times u length times sine theta. Okay, if the u parallel v, what is theta here? Theta is pi or 0, right? You can take one of these. We don't exactly know since they are parallel to each other. They didn't give us the direction of those. So they might be in the same direction or in the opposite direction, but we know that they are parallel. That is why u times v times sine 0, as you see, it is 0. So we will say that if they are parallel to each other, the cross product is going to be 0. The magnitude of the cross product can be given. Let's take the magnitude of this one. Let's not forget the n here, right? Let's not forget the n. That's my bad. But it doesn't matter since we just multiply by 0. So the magnitude of u times v, how could I find that? U length times v length times sine theta times n length. The only thing, we can predict here the length of the n. What is the length of the n, guys?
1.
1, since we said that that should be unit vector. So the cross product of u and v could be equal u times v sine theta. Now, another example, guys. I want you to calculate all these. There might be some other version, but that's fine. Okay, who is going to help me? What is I cross product I?
0.
0. Why?
A vector cross with itself is 0.
But why?
They're parallel to each other.
Exactly. They are
Yeah.
parallel to each other, right? Because of the previous result. They are parallel. That is why 0, since we know I parallel I. What about I times J?
It's K.
It's K. Why? Let's take a look at it.
Because by definition, I and J are
I and J are both
Let's-
perpendicular to K.
yes.
Exactly. If you okay. Let me clear this part. And if you look at the 3D space, so this is my I, this is the J, as you see, right? What I'm looking for a vector which is perpendicular to these two vectors, and then it should be unit vector. So it is obvious to see it is K from the geometry. But let me see, right? From here, sine pi over 2 times n. I length is 1, J length is 1, sine pi over 2 is 1, right? And now 1 times n. As you see, n should be chosen here, which is obvious, right? I can choose the K. This comes from this definition, but if we use the second definition, I'm gonna give you soon, okay? We can directly prove that, actually. I don't wanna use that definition right now, but soon we are gonna use, okay? How we could calculate all these using the determinants. All right. What about, now I want you to tell me, after saying the I times J, okay, I times J is equal K. What about J times I?
That would be negative K.
Eli says it is negative K. Do you agree with him?
Yep.
Yes.
Do you want to explain why?
The way I visualized it is using the right-hand rule.
Exactly. The right-hand rule. The right-hand rule says, now, guys, look at that. This time I started by J. That is why the angle should go, right? Should go the other way around. My bad, actually, the first time I need to do the other way around. Please forgive me. I times J, the angle was this one. That is why, right, because of right-hand rule, my thumb should show the right above. But this time, look at it. If I start by J, so if I use my fingers, right, from J to the I, this time the perpendicular vector is gonna be this vector because of the right-hand rule. And then this vector, perpendicular to the IJ, is gonna be opposite, is gonna have the opposite direction with K, which is negative K.
Professor?
Yes.
So for the right hand rule, just to clarify, so basically we take our fingers, we go around the direction that we want to go, and this becomes the
Exactly. Let me show it to you in this way. Again, this is I, J, all right? And then look at that. So this theta, my finger should be on the same direction with the theta, okay? So you need to show the same direction. When you show the same direction, your thumb, where your thumb shows, that's going to be the direction of the cross product.
I think before when you were writing U and V and then U cross V, it went the other way, but I'm not sure. If you go up to
No, we did the same thing. Look at
right there, so like your theta goes around this way, so shouldn't it be down?
Yeah, I start from U to the V, same.
Right. So shouldn't it go down?
No. Where do you, okay, the problem here goes, okay, no. If you say this is U and V, I do the same thing, U and V. I start my theta, okay, from U to the V, all right? So U times V, I'm trying to find out the U times V.
Mm-hmm.
If I start by U, if I end by V, okay, my theta should start from U and it ends at V, all right? So
Right.
the product now will be the vector which is perpendicular to, okay, this way. Did you get that?
Right.
And your other example, you had the arrow pointing the other way, or the theta arrow.
Yeah.
Well, V and U had swapped places in the other example. So
Yeah,
right
so-
hand would have had it going down, I think, if I'm visualizing it correctly.
Yeah, so your theta goes from U to V, which means you're right.
But still I start from U, look at that. That's my,
Right. But
Yeah, if you start from U and go to V, then your
Yep.
thumb would be pointing down.
yeah. So, it goes
So
like
U
that.
cross V should be pointing down rather than up.
For
So
that
you-
specific
we should
example.
do it
Right.
this way, UV,
Yeah. And then it goes that way, and then it's positive. Yeah,
Right.
yeah.
all right. Let's fix that. Sometimes when you say the right thing, but you do the other way around. That is why J times I is gonna be negative K. All right? So with the same consideration, okay, can we just say what is I times K?
Negative J.
J. K times I, K times I,
Negative J.
negative J. K times K,
0 because it's parallel.
exactly, they are parallel. So
Isn't
table, right? I times J, we already did that. And then there are two other versions actually, K times J and then J times K. As you see now, it is gonna be the I and then negative I. Sorry, the other way around, I and negative I.
I thought I cross K is negative J.
Say again?
I thought I cross K is negative J.
I cross K is J.
I thought it was negative J, because if you do the right hand rule from I,
Yeah, shouldn't it be negative J?
I agree with that.
yeah.
I cross K is, yeah, still I am taking all right. You are right, guys. Negative K, and then K times I is equal J. Since, again, right, I times K, yes, it should be this way. You are right. All right, we will be using these actually, multiplication in some problems, okay? And then it is gonna make our job easier. Now, we have some features about the cross product. I'd like to share them with you as a theorem. But the proof of these features actually is not so hard. The first one, if you have two vectors and if you commute them, okay, the negative you will have in front. So that is how you can apply this feature to the previous example as well, right? You multiply I times j, which is k, but if you would like to write the switch to j and I from this feature, you can just say, okay, this is definitely just gonna be right, negative k.
Shouldn't the right hand of that say negative v at cross u?
Say again?
Shouldn't the right hand of that say negative v cross u? Because you wrote u cross v twice.
Yeah, I am writing wrong. Sorry, my bad, guys. Of course. Thank you for fixing. And you can distribute, guys, over addition. We say the correct, but we wrote wrong. U times V plus U times W. The third rule, you can do the same thing from the right-hand side, but that doesn't mean we can multiply the three vectors using the cross product and then they are going to be same. And also you can move around the constant actually, or you can ignore it, okay, at the beginning and then multiply it later. So here the U, V, and V are vectors, okay? But the C is constant, guys. C is constant. The first application of this cross product, guys, is the area of parallelogram. Is the area of the parallelogram. So we can use the definition of the cross product to calculate the area of the parallelogram. How could that be? Let's say I have two vectors, U and V, and then I have the theta here. I'd like to calculate the area of this parallelogram. Could you please remember what was the area of the parallelogram you saw at high school?
Base times height.
Exactly, right? This is height. This is, let's say, base. So base times height would give you the area. So what is the base and then what is the height here? The base length here, as you see, right? The base length is the length of U. So I can use the base length as the length of U vector. So what about the height here? This height vector can
So
be
V times sine theta.
exactly. Right, the length of the height can be given by sine theta. So the area, right, area of the parallelogram is going to be then base times height. So base is equal U and V and sine theta. as you see, what you see on the right-hand side, right? This is the magnitude of the cross product. Is that all right? This is the definition of the magnitude of the cross product. It is not just a cross product. So the area can be given by this formula then. All right. So you need to multiply the two vectors using the cross product and then take its magnitude. It's going to give you the parallelogram area between these vectors. As you see, I can apply the cross product to the geometry as well. Let me give you a couple examples before we proceed, guys. Okay. Example. Find the area of parallelogram with vertices A, -3, 0, B, -1, 3, C, 5 to the 2, and D, 3 to the -1. Would you like to try it?
Professor, A is 3, 0, right?
Exactly. -3, 0.
Okay. Okay, thanks.
What is the first number in C?
5. But there is a problem here. I missed that one. Can we just calculate the, yeah, you will notice that if we would like to use this definition, it requires us to have what? The theta, right? But there is no theta around actually. So that is why you need to be given, or you need to find the theta. But at least, all right, we will solve this question. We will solve this question, but at least, okay, let's see this part. Since the vector I'm gonna take, like in the definition, is gonna be this vector first. If you would like to say you can say that. This is the vector you would like to take, AB, right? And then V, you might take this vector. So the multiplication of these two vectors, and then magnitude of these two vectors, right, by cross product, should give you the area. Yes, that's the observation we can make. But as you notice that, this example actually shows me a requirement of something. Requirement of what? You need to be given the angle, but you don't have the angle. That is why, right, you need something better when you are not given the right angle. Can we create another definition for this one? Let's try it then, right? Just keep this question in this way, since we're gonna come back. As you see, there is a problem here, right? We need to solve. The normal definition, right, couldn't help us to solve this problem. That is why we need to create another definition. But after giving that definition, calculating the parallelogram is gonna be easy again. So the determinant formula for u times v. This time, I would like to have a determinant formula, which it is gonna be given by the determinant formula, but I wanna have a component form for the u times v, guys. What do I mean by component form? You will remember, right? In the dot product, I use the component. This time, since I know that cross product is a vector, I'd like to have something like that. Look at that, K1, K2, K3, such a thing. It should be given by component form, not in a way, right, I used in the first definition. That is why I'm gonna take a look at, okay, the original meaning of the cross product. So U is equal U1, U2, U3. And V is equal, as you know, V1, V2, and V3. And also, I can write the U in this way, U1I, U2J plus U3K. And then V is equal V1I, V2J plus V3K. How could I multiply, right, these two vectors then? U1I plus U2J plus U3K times V1I, V2J plus V3K. So in this manner, right, I'm just gonna use this cross product in the normal way, guys, in the regular thing. What do I mean by that? I'm gonna distribute each term in this way. Let me do this calculation. Let's do it together. U1I times V1I, U1 times V1, I times I, plus U1 times V2, I times J, plus U1 times V3, I times K, plus, now I'm at the U2J term. I'm at this term. Let me use different color. Now I'm gonna multiply this one. This is gonna be U2 times V1, J times I, plus U2J, U2 V2J, J, U2 times V2, J times J, and U2 times V3, J times K. I still have another component. This component. That's gonna be in this way. U3, V1, K times I, plus U3, V2, K times J, and U3, V3, K times K. All right. I'm done with the multiplication, but now let's arrange all the terms. First of all, I times I is 0, so that's why this term is 0, this term is 0, and then this term is 0, all right? And I know how could I multiply, right, these cross products. I times J is equal K. I times K is equal, guys, negative J, right? Negative J. J times I, negative K. J times K is equal I.
I.
K times I,
J.
J. K times J, I. So now, K times I times K, yes. let's correct the k times j times k. One of them should be negative. I have negative. All right. Now I have, right, the like terms around. I can bring them together. As you see, this is k term, this is k term. So in the parentheses of k, what I have, u1 v2 minus u1 v2 minus v2 v1 u1 v2, yeah, u1 v2 and u2 v1, u2 v1, right? And what else I have? So I'm done with these terms. Under I have u2 v3. Let me write it down in this way so that I can have more spaces. u2 v3 minus u3 v2 times I, and j, for the j, what I have, u1 v3 minus u3 v1 j. All right, did you see that? Now that is gonna be my cross product. As you see, it is in the right, the vector notation, it is in the component form. I have three components, I, j, k. So the coefficients of these components, as you see, right? These are the coefficients. But the problem is here, knowing this in this way, or the memorizing this formula, okay? This is how we derive the formula. This is gonna be the exact definition of the cross product, guys. So you might take this one actually now as a definition, another definition of the cross product. But what I don't like about this, the formula itself. As you see, it is hard to use this formula in this way. I will try, okay, another way to make this formula compact so that I can use different form to calculate the cross product. That's why, okay, we will be using the determinant form to calculate cross product. How many of you actually took the linear algebra before this class?
I did.
You did, Sam. How many of you?
Mhm.
What about, how many of you have you seen the determinants at high school? None of you? 1, 2, 3, all right. Just some of you. Okay, anyway, it is not so hard. I'm gonna give you the definition of the determinant. So now these all actually some notes from the linear algebra or the high school calculus classes, if you took similar classes. A general 2 times 2 matrix is of the form. This is how you can give them matrix in this dimension, 2 times 2 matrix, guys. We usually look at the square brackets. So there is an important feature about this matrix, guys. We call it the determinant. We mostly use, okay, this determinant, okay, to simplify this calculation. The determinant of this matrix is this, guys. This time I look at just the line, okay, around A, B, C, D, 2 lines, and then determinant will be given in this way, AD times minus BC. You just multiply A by D and then B times C. You just subtract them, guys. That is what we call the determinant of this matrix. Multiply A by D and multiply B by C and then subtract them. But if you have the 3 times 3 matrix, That's not easy. And then we will need the 3 times 3 dimensional matrix actually. A general 3 times 3 matrix. By the way, this 3 and then 3 shows me, okay, how many rows I have and then how many columns I have in my matrix. As you see here, I have 2 columns and then 2 rows in 2 times 2 matrix, guys. That is why it is called 2 times 2 matrix. In 3 times 3 matrix, I have 3 rows and then 3 columns. So 3 times 3 matrix is of the form in this way. A1, A2, A3, B1, B2, B3, B1, B2, B3, C1, C2, C3. And then again, the determinant, this is the matrix. Of course, you can do a lot of things with the matrix, but the determinant is just one of the features of the matrix. The determinant of this matrix is given by or is defined in this way. In this way. A1, A2, A3, B1, B2, B3, C1, C2, C3. I just used the line to show the determinants, guys. Okay? So, what it will be in this way. A1 and the determinant of the smaller matrix inside this big matrix. Minus A2 times B1, B3, and C1, C3. And plus A3, A3 times B1, B2, B1, B2, C1, C3. Yes, you are right. The notation sometimes might go wrong. B2 and C2, guys. The first, please fix it. So basically what you do here, you take the...
Professor, isn't the last one, the bottom right-hand side, a C2?
Yes, that's the C2 as well. What you do, guys, you just cross the line, okay? You have A1, and then you look at that, this determinant goes here. All right? And then you do the same thing for A2, look at that. I can show it to you to make it easier. When you take the A2, you cross the line, row and then column, you have A2, and then the rest, the rest goes here, guys, to do this determinant. And then you do the same thing for A3. A3, just cross out the right column and then row, you have A3, and then the rest, right, will form another determinant, and then that goes here, guys. That is how we construct actually determinant when you have the 3 times 3 matrix. All right. But my problem was to calculate, right, the cross product using the determinants. What you see here, guys, exactly what we found. In this formula. Let's go back here. You see this formula? Don't forget, this formula is exactly the determinant of the 3 by 3 matrix. Now, I will give you the determinant formula for the cross product. Again, the definition of, right, U times V this time can be given in this way. I found the formula in this way, guys. U2, V3, I'm gonna write it down again. U3 V2 I plus U3 V1 minus U1 V3 J plus U1 V2 minus U2 V1 K. Now, as you see, like in the determinant, the definition of the 3 by 3 matrix, this I, J, and then K, right, are like the A1, A2, and then A3. You see, A1, A2, and 3. That is why they will go, or maybe we can do one more step. You can write this one this way. I times U2, V2, U3, V3. Look at how I am writing. J is equal U1, V1, U3, V3. But look at that, since I have the other way around, U3, V1 minus U1, V3, that is why you need to make this one negative. All right? You need to make this one negative. I can just adjust the term in this way, negative, and then I can make this one negative, okay, to correct the definition. And then also K goes here, and then the determinant of this one, U1, V1, and then U2, V2. As you know, this is given, right, in the determinant in this way, I, J, K, right, I, J, K. And then U1, U2, U3, V1, V2, V3. So that is how the cross product can be given in another way. This is called the component form of the cross product, guys. Component form of the cross product. Did you see? I found a new way to calculate the cross product without using the theta. Without using the theta. Now the definition actually at the beginning can also be derived from this definition. This is the main definition actually, using the determinant. And then this determinant made my, right, the complicated formula easier, right? At least, right, how I notate it. You see, this is the formula, but now I made it so compact in the determinant form. That's the basic understanding of the cross product. So let's go back to the right, let's go back to the parallelogram problem then. Can we calculate it now?
Yes.
Exactly. But first, I need to figure out what is AB vector. AB vector. To calculate the AB vector, right, I need to use the A and B. And I'm going to write the subtract the component starting from the right, the second vector. -1, -3, it is going to be -3. It's going to be 2. And 2 to the 2, 3, 0. Right?
That's what I got.
Yep. Perfect. AD is going to be 6, -1, 0, right?
Yep.
Exactly. Since it seems they are in the same plane, of course, to create the, that's why the third component is 0. Now, look at that. Using the determinant form, guys, A, J, K. AB vector, like the U vector, will go here, 2, 3, 0. AD vector will go here, right? The 6, -1, 0. I know I need to, right? I need to multiply these two vectors using the cross product. And then I know now I can do this job using the determinant. Can you please help me now how I am going to calculate this determinant? Saying, look at it, I times the smaller determinant inside, right, the bigger determinant. This one.
Because both k components are 0, can we not
Exactly.
just overgo I and j?
Yes, but I'd like to show everyone, Ali. That's why I'm doing in detail. -1, 0. But you say the k component 0, but we need to have the 3 components since the cross product, right, is given in the 3D dimension. Also, for your question. Negative now, j. For the j part, look at that. I will use this determinant, guys. 2, 6, right? 0.
Mhm.
I will cross out this part. So 2, 0, 6, 0. And plus for the k part, let me use different color. For the k part, k times
2 free, 6 -1, right?
exactly 2, 3, 6, -1, 2, 3, 6, -1. Now remember, please, if you have the right 2D determinant, how you could multiply, how you could calculate 3 times 0, 0 times -1, right? Just do the cross multiplication in the determinant, which is going to be 0. Same, look at that, 2 times 0, 0 times 6, add them, it is 0. But when it comes to the k, right, it is going to be what? 2 times -1, -2. 6 times 3, it is -18, but I have to write the negative in front. It is going to be -18 times k. So it is going to be -20k, but as you know, for the area, I need to take, right, its magnitude. Since k is the unit vector, the magnitude is going to be 20. So now I found, right, the area of the parallelogram. Are we doing all right? Did we get the second definition, guys? How do you feel about it? Thank you, guys. Thank you, Ben. Thank you, Andrew. Thank you, Ali. Thank you, Abby. Thank you, Wilson. I don't see a lot of people, everybody close, hide their face, guys. Do you all have camera problem today? All right. Now we are ready to solve more problems, guys. We are ready to solve more problems. As an example, since we just did one example, but I want you to solve one more, okay, using the determinant. Can you please multiply these two vectors using, right, the determinant form? And then let's see how you got it. All right, you have two vectors, and use cross multiplication to multiply them, but using the second definition.
The vectors are 1, 2 free and 1, -1, 2.
Exactly.
Is it 5?
Is that 5? But you need to give me a vector, guys, right?
7i, 1j, -3k. Whoops.
Exactly.
Okay.
Since the cross multiplication is a vector, right? Let me see how many of you found the same thing.
I got that.
Good, good, good. What about the guys without camera? I don't see them. At least, okay,
I got it.
raise your hand. I can see, okay, how you are doing there, guys. Are you doing well? Are you sleeping? Are you joining class? Are you what are you doing there? So, all right, I got it. Still working through it. All right, guys. Another question coming. Another question. Let's check it out. A couple different things now. A couple different things.
Why is it 7i? Shouldn't the 3 be multiplied by the -1, making it 2? Or -3, so it should come out to 4 plus 1 and 5i?
You have to subtract.
This,
Oh, got it. Thank you.
yeah. A minus B times A plus B is equal 2 times A times B. Can you prove it? You just need to use the features of the cross product. Distribution feature first. Let me help you a little bit. You can distribute, right? Over addition.
Is that supposed to be a negative? Is that supposed to say A minus B?
This is A minus B, yes.
Okay.
Can you help me at this step, guys? Now, as you see, I just distributed. It says, right, I can distribute first the A times A plus B here I'm gonna have. And also negative B times A plus B I am gonna have. I can do it one more time, right? I can distribute one more time. Still, this is the distribution of cross product over addition. That's what I do here. But now I need your help. What is A times A?
0.
0. Do you all agree, guys? You should be able to see, right? Right
Yeah.
away. Thank you, Sam. So this is 0 because they are parallel to each other, right? This is 0. And then B times B also 0, right? So what am I gonna do with this? So now, is this 0?
No, it's not, because minus b times a will be a times b.
Exactly, guys. You should notice that from here, actually, we saw that b times a, right, is not equal a times b, right? There is no such a feature. If it was, that would be 0. But remember, right, we had a commuting feature in this way. If you have the negative b times a, that is already equal a times b. We know that. We just discussed right at the beginning. So now you can add them to a times b. And then that's what we need, right? So now we prove that. Another example. Find the area of the triangle with vertices P1 for 6, Q -2, 5 -1, and R1 -1, 1. So this time it is not about the parallelogram, it is about triangle. But can we use a parallelogram area definition, guys? Let's say this is P, Q, right? This is PR. That's the triangle area you should be finding. How could you calculate that area?
You just find the area of the parallelogram and then divide it in half.
Exactly. That's what you need to do. So this area, right, is equal the parallelogram divided by 2. And then we know that then it is going to be in this way PQ times PR cross product magnitude divided by 2. I will just give you the determinant, guys. I'm not gonna spend my time, okay, with this operation this time. Please do the determinant part on your own. So if you multiply PQ and PR, okay, using the determinant formula, it is gonna give you -40, -15, and 15. And if you take the magnitude of this vector, the result is going to be equal 5 square root 82. 5 square root 82. Last thing for today, guys. There is a physical quantity which we can use cross product to calculate, which is torque. So as you know, torque is the measure of the tendency of a body, right, to rotate about the axis. You apply, right, your force. Let's say you apply the force, right? You have a stick here, like a stick. It might be anything. And this length of this stick, right, is R. If you apply this force about this point, the torque can be calculated by this. Of course, if you have the, right, if you apply the force directly, perpendicular, in a perpendicular way. But let's say if we apply the force, right, if we apply the force, not in that way, in this way, let's say you apply the force in this way, generally, we do in this way. Like you close the door, when you close the door, you apply your force, right, with an angle. The theta between your force and then R is gonna be your reference angle. To get this formula, as you see, to get this formula, I'd like to have, right, I need to have, sorry guys, this should be the cross product here. But you are gonna see this cross product where it comes from, actually from this discussion. I need to have, right, this component after the y component. After the y component, as you know, it is gonna be F magnitude times sine theta. This is the first component which it has effect on the stick, right? It should be perpendicular to R. When I multiply, right, this force by the magnitude of the R, that is gonna give me, right, my torque vector. All right? As you see, right, since this vector f of y, it is already, right, a perpendicular vector you can get. If you look at here, that is the definition of, right, exactly the cross product, which that is why you are given in physics, right, in this way. I just have 1 minute. I'm not sure if I can finish it. As an example, a bolt is tightened, look at that, guys, tightened by applying a 40 Newton force to a 0.25 meter range as shown. In this way, guys, look at that. I have a bolt here at this point, and then I have the range, but the theta, sorry, my theta to rotate this one is 75 degree here, and then this is the 40 Newton, and then this distance is 0.25 meters. So if you would like to, okay, calculate the torque, we will be using the same formula, guys. R F sine 75. If you multiply all of them, 0.25, 40, and sine 75. So it is gonna give us the torque magnitude, torque force, guys. Of course, if you would like to, okay, take the vector as a vector, you could do that without taking the magnitude. All right, guys, I don't want to get your time more. So let's stop here. Okay, see you next week. If you have any question, I have office hours. Please join me, okay, in my office hours. I can help you with the assignments or all other things. Have a nice one. See you next week.
Thank you.
Have a
Goodbye.
nice
Professor.
day.
Thank you.
Thank you.
Thank you, Professor.
Thank you. Have a good day.
Thank you, guys.